I'll be walking through this guided note sheet on integration steps, so have this document handy and you can take notes directly on it. Okay, let's integrate a polynomial. Integrating a function means finding the area between the function and the zero axis. We'll start with the function to integrate, so we'll use this example velocity function for an object moving in 1D. We have 5 steps to work through. 1. Write a derivative relationship between the function you have, v, and the function you want to find, the position, x. So write this on your page first thing. State that derivative relationship. Next, rearrange that into 2 integrals. So multiply both sides by dt to rearrange this into dx equals v dt. And then express each side as an integral, meaning a sum of an infinite number of infinitesimal changes. So you'll write our integration symbol on both sides, indicating that you're going to be summing up an infinite number of dx's, which means summing up an infinite number of v dt's. So now you have 2 integrals to solve. On the left-hand side, the independent variable, IV for short, is x. On the right-hand side, the independent variable is t. So there's our independent variable, the x and the t. The left-hand side integral is easy, so it's really the right-hand side integral that takes a bit more work. That's where we'll focus. At this point, you could substitute in the function vt into the integrand. That's the meat in our integral sandwich here, the part between the integral symbol and the dt, the integrand. So that is our integrand. We can substitute in our velocity function from above. So this is our example polynomial. So let's put that in for the velocity function here. That is our integrand. So we have step 2 rearranged into 2 integrals. Okay. 3. Set the limits of integration, meaning the starting and ending values of the independent variable t, time. So now here we have 2 options depending on what it is that we want to know. So option A. Find a single numerical value, delta x, that represents the area under the velocity graph between a fixed lower limit x1 at time t1 and a fixed upper limit x2 at time t2. So if this is our velocity graph, this cubic function, and what we want to find is the displacement between some starting time and some ending time, t1 and t2. So the displacement will be the difference between the final position x2 and the initial position x1. If that's what we want to find, this specific area between these 2 specific times, then we write in the limits of integration like this. We put t1 here as the starting value of time and t2 there as the final value of time. Then on this side, x1 as the starting value of x and x2 as the ending value of x. So we must have agreement between our upper and lower limits. t1 is the value of this independent variable when x1 is the value of that independent variable. And likewise for the upper limits, t2 is the value of this independent variable, time, when x2 is the value of this independent variable, x. Okay, so that's our setup here, but before evaluating this definite integral with these fixed upper and lower limits to find this fixed specific area, before evaluating this, let's talk about our other option. Option 2 would be to find the function x of t. We've got our velocity function, v of t, this polynomial. What if I want to find x of t, the position function? So rather than finding some specific displacement, some specific area, I want to find the actual position function. Okay, so we can do this. This function represents the area under our velocity graph between some fixed lower limit, some initial position x naught at some initial time t naught, and a variable upper limit, x as a function of time at some variable future time t. So that picture looks like this. Here's our velocity function once again, and we'll fix some starting time, t naught, at which we know the position. So if we know your position, x naught, at time t naught, this starting time, then we're going to let the upper limit here be a variable. So we can imagine sort of shifting this time back and forth so we get different areas. So if we can pick any value for t, we get different areas and find the corresponding value for some variable future position. So here in our limits, what we've done is set t naught as the initial value for t and x naught as the initial value for x. That's our fixed lower limit. But then for our upper limit, we're just saying t here, some variable future time t, and then over here we'll have some variable future position x. So t naught is the time when position is x naught, and t will be some future time when the position is x. So you see we've got these two ways that we can choose our upper and lower limits depending on what we want to know. Do we want to know some particular displacement, some particular area, then fixed upper, then fixed lower and upper limits? If, on the other hand, we want to know the function x of t, we take a fixed lower limit and a variable upper limit. Okay, so we'll come back around to evaluating the integral with these two options. Either way we do it, option 1 or option 2, we'll need to employ the fundamental theorem of calculus, which means we need to know the antiderivatives of the integrand with respect to the corresponding independent variable. So let's talk about finding the antiderivatives. Okay. First, the right-hand side. The left-hand side. There is an antiderivative to be found over here. Now, you know that if we sum up all the dx's, we just get the total delta x. That's the result on the left-hand side. Sum all the little changes, all the little displacements, we get the big change. But if we want to be a little bit more technical about it, let's go way back up here, up to this stage, and say that when we have dx equals v dt, I know I can say 1 times dx without changing anything. So there's a little 1 there. So 1 times dx, 1 times dx, carrying that through. 1 times dx, 1 times dx. So on the right-hand side, our integrand is this velocity function, this polynomial. There's our integrand, the polynomial. On the left-hand side, we actually have an integrand. It's just 1. 1 is the integrand here. So if we want to find the antiderivative of this integrand with respect to x, let's note that suppose y equals x. We have some function y equals x. Then dy dx equals 1. So if I take the derivative of x with respect to x, I get 1. Which means if I take the antiderivative of 1 with respect to x, I should get x back again. So the derivative of x with respect to x gives us 1. The antiderivative of 1 with respect to x gives us x. So here the antiderivative of 1 with respect to x is x. But of course, we know that our antiderivative must always include a plus c. So x plus c is the antiderivative of this hidden integrand inside here with respect to x. Now let's look at this polynomial. We know how to find the antiderivative of this integrand over here. This one's being found with respect to t. time. So time is the independent variable on this side. And we have a rule. So we're going to take it one term at a time. 5t cubed, we know to take that 3 and add 1 to it. So we get t to the 4th, and then 5 divided by that new exponent. So 5 quarters t to the 4th. Then for this term, this is t to the 1 right here. So we add 1 to that. So t raised to the power of 2, and then divide the coefficient by that new exponent. And then here on the 3, we know there's a little invisible, unseen 3 times 1, so a 3 times t to the 0 there. Sorry, that's so small, but 3 times t to the 0, because t to the 0 is 1. 0 plus 1 is 1, so we get a t to the 1, and then take the coefficient 3 and divide by the new exponent. Let's simplify that. So the antiderivative of this polynomial with respect to time will be 5 quarters minus t squared plus 3t, and then once again we'll have to add in a constant, c. Now in general, this constant over here has nothing to do with this constant over here. They should be different constants. Let's call this one c prime to show that it's some other value. Okay. So in summary there, the antiderivative of the left-hand side with respect to x is x plus c, and the antiderivative of the right-hand side with respect to t is this function. And then here's the connection we have to make. If the velocity is the derivative of x, position, then the antiderivative of velocity is position. And so this function here, the antiderivative of the velocity, that must be our position function. So this is the antiderivative of the velocity, and the antiderivative of the velocity is position. Therefore, this function is our position function. And once more, we know that there's a constant term on here, and I don't know that this constant is the same as that constant or that constant. So let's just call this c double prime, just some other constant. The point is we have some constant term added on here. All right, so we found our antiderivatives, and now we're ready to apply the second theorem, the fundamental theorem of calculus. I'll pause here just to break it up.